Good morning, my dear students. Recently, we had finished Newton's three laws of motion, including applications and numericals, up to the level of NEET, JEE, or CET. Now, let's continue the chapter called Force and Laws of Motion. The next topic for you is Law of Conservation of Linear Momentum. What is that? Law of Conservation of linear momentum. Law of conservation of linear movement. About linear momentum, in-depth analysis we had done already. So the linear momentum is the product of mass into velocity. This already we had done so many numericals on this even. Before going into the topic, let's recall the concept called law of conservation of energy. This you might have studied in 6th standard or in 7th standard. Law of conservation of energy states that energy neither be created nor be destroyed. We cannot create the energy, we cannot destroy the energy. But one thing we can do is the energy can be transformed. Energy can be converted from one form to the another form. Electrical energy can be converted into the sound energy. Clear? For example, I have told you. So energy neither be created nor be destroyed. It just converts or takes from one form to the another form in the same way. Law of conservation of linear momentum. So this is the linear momentum. We cannot create or we cannot destroy. So linear momentum neither be created nor be destroyed. I'm just writing the same. So this is the linear momentum. Neither be created nor be destroyed. It just transfers from one body to the other. It just transfers from one body to the other. Example also I have given you. Clearly I had mentioned. So imagine this is the ground. There is a ball of mass m which is dropped. Dropped means initial velocity is 0. And it will reach to the ground with some linear momentum which is mass into velocity just before striking the ground. What is the linear momentum exactly if it is having m root 2gh if it is dropped from a height h? So many problems also we have done on it. So this is the linear momentum contained by this body just before striking the ground. After striking the ground, what happens? After striking the ground, the same amount will be transferred to the ground. If the ground is made up of a glass material, when this ball drop on the ground, the glass material will definitely break. Understand? It will collapse just because of the transferring this much of quantity of motion to the ground. Understand? That quantity of motion only will destroy the surface. Clear? So that's a concept of linear momentum and transfer of linear momentum. So only thing takes place is transfer of the linear momentum. There won't be any loss in the linear momentum, in the total linear momentum. Okay, so that's what it says. Neither be created nor be destroyed. There's no loss, but it just transfers from one body to the other. One body to the other. That's it. Clear? Let's see. So what exactly tells this here? Total linear momentum of a system is constant. So that's what the simple meaning of law of conservation of a linear momentum. Total linear momentum of a system remains constant. So these two definitions together I can write. For example, there are two bodies. So one is mass of the body, the another one is the ground. Okay, there are two bodies, body and the ground. So in the same way, these two together, what I can write here, total linear momentum before the collision is equal to total linear momentum after the collision, right? This is also equal to the law of conservation of linear momentum. There won't be any confusion at all. This and the last one, all three, it gives you the law of conservation of linear momentum only. Okay, let us justify this part. Justify this part. It's so simple to justify. Imagine I have two bodies. This is the first body of mass m1. Initially, this is the body is moving with a velocity u1. So I have another body of mass m2 and its initial velocity is u2. For example, assume the situation, initial velocity of the first body is more than the second body, right? What is our assumption here? This is the body is moving faster than this. This is the body is moving faster than this, right? So after some time, obviously there is a collision takes place between these two bodies. So that's the point I am drawing here. So this is the first body and second body of mass as m1 and m2, and see here there is a collision is taking place here. After the collision, definitely they move with some different velocities. After the collision, so this is the first body of mass m1 moving with a speed or velocity v1, and the second body of mass m2 are moving with a speed v2 here. So this is the situation is happening before collision. What is that? Before collision. And this one during collision. During collision. And the last one is after collision. This is the situation. After collision. If you carefully observe the situation here, there is a linear momentum for the system. Here, the system is the combination of two bodies. Okay, so this is the system. This is the system. System is the combination of two bodies. And these two bodies will have the total linear momentum. What is that? Total linear momentum of this, linear momentum of the first body and the linear momentum of the second body. So linear momentum of the first body is what? m1 u1 plus, so what is the linear momentum of the second body? m2 u2, right? What exactly meant by this sum? This is called total linear momentum before the collision. Yes or no? Tell me, the total linear momentum, yes or no? Yes, total linear momentum before the collision is m1 u1 plus m2 u2. This is the total linear momentum of the system before the collision, right? After the collision also, there is a total linear momentum that you can check here. Total linear momentum of the system after the collision is m1 v1 plus m2 v2, right? The sum of the system linear momentum after the collision, m1 v1 plus m2 v2. See here, m2 v2. So this is the total linear momentum of the system after the collision. Okay, see, there is a justification for this statement. Total linear momentum before the collision is equal to total linear momentum after the collision, and this is what the justification is done here. Now let's focus on during the collision. Let's focus on during the collision. During the collision, what happens? That's the most interesting part here. During the collision. So during the collision, what happened? There is a transferring of linear momentum takes place from one body to the another body. That's what I told you here. When this body is colliding with the ground, the linear momentum will be transferred without loss of the total value. For example, linear momentum here before the collision is some 100 kg meter per second. Okay, what is the SI unit of linear momentum? It's a mass into velocity, right? Kg, velocity is meter per second, right? That's what I told you. For example, before the collision, the linear momentum of the system is 100 kg meter per second. After the collision also, the linear momentum of the system will be 100 kg meter per second. Irrespective of this V1, V2 values, you will get the total sum here and here will be same as 100 kg meter per second, right? So don't ask me, always will it be 100 kg meter per second? No. Clear? So just an example I have taken. Whatever the linear momentum of the system before the collision, the same will be satisfied after the collision also. That's called law of conservation of linear momentum. Let us focus more into the more deeper levels at the case called during the collision, right? Are you ready to focus more at during the collision condition? Yes or no? Yes, right? I can hear. So during the collision, let's focus more. See, during the collision, what happened? This body will apply some force on this, right? What is that? Force on the second body due to the first body. And at the same time, action-reaction forces takes place here, and the second body will also apply some force on the first body here, force on the first body due to the second body. As these two are action-reaction forces, what I can write here, action-reaction forces, F21 is equal to minus F12. So this is what during the collision takes place, right? Action is equal to minus of reaction. So you can consider this is action or this is reaction. So it doesn't matter here. But two forces, both are equal and in opposite directions. Okay? Clear? Now, look at here. F21, force on the second body. Force on the second body due to the first one, which is equal to minus force on the first body due to the second body. Okay, so let's take this one, F21. F21 is force on the second body. They are talking about second body. So second body mass is M2 into second body acceleration. What is the second body acceleration? Second body's final velocity minus second body's initial velocity. So V2 minus U2 by time. Both are colliding at the same time. Yes or no? T, which is equal to minus force on the first body due to the second body. Force on the first body. First body only will accelerate. Understand? Clear? Force on the first body. For example, there is a collision between a lorry and a bicycle. Lorry is colliding a bicycle, so definitely bicycle will accelerate. Yes or no? Because force on the bicycle due to the lorry. Understand? Bicycle will accelerate. The same thing here. Force we are applying on this body will accelerate. Now the force is applying on this body will accelerate. So M1 into, so first body's final velocity is what? V1 minus first body's initial velocity is what? U1 divided by T. Okay, clear? So T cancel here. So I can elaborate this one. M2 V2 minus M2 U2, which is equal to minus M1 V1 minus of minus plus M1 U1. What we are doing actually here? We are just focusing more on the case called during the collision what happens. Okay, so during the collision what happens, let's check one more time here. Let's continue. All U1 all initial velocity terms, let's write one side. Okay, so this is M1 U1, here minus M2 U2 is there, so let's write the other side. Here V1 and V2 final velocity terms, we write the another side. This is minus M1 V1 goes to the other side, that will be plus M1 V1. Okay, so this one M1 V1 plus M2 V2, which is equal to the right hand side m1 u1, I'm just keeping it as it is, m1 u1 plus, and what is this term, minus m2 u2 goes to the other side, that will be plus m2 u2. Clear? So now what I can write finally, m1 u1 plus m2 u2, which is equal to m1 v1 plus m2 v2. Okay, clear? So this is the concept, this is what the derivation for law of conservation of linear momentum. Just by observing the statement, we had written total linear momentum before the collision is equal to total linear momentum after the collision. By focusing on this case during collision condition, we could derive the same expression. Okay, so there are so many applications involved in the law of conservation of linear momentum, and this is one of the most important topic for the NEET exam, JEE exam, and even for CET exams. One of the most important topic, right? And so many applications are involved in this, and let's discuss about one by one about applications. So my dear students, we are going to discuss majorly three applications related to the law of conservation of linear momentum. And let's see, what are the three applications first? Number one, recoil velocity of a gun. That's a first application we will be doing. And number two, rocket propulsion. And number three, common velocity. From these three applications, most of the times there were questions in NEET exam, JEE exam, and CET exam. That's the reason three applications are important, right? Let's start. A recoil velocity of a gun. What is this recoil velocity of a gun actually? Let's understand this with a simple and basic diagram. I have told you already that this is, assume that this is a gun. Don't consider that it's a pipe, right? Assume that it's a gun. So mass of the gun is m2, and there is a bullet inside I'm talking about bullet inside whose mass is m1, right? So look at here. So what I am writing, m1 is mass of the bullet, m2 is mass of the gun. Okay, and before firing, initial velocity of the gun and initial velocity of the bullet will be 0. Yes or no? So let me write u1 is initial velocity of the bullet, everything, the first case, first component and first object we are taken as a bullet. That's the reason m1 is for bullet and u1 is also for bullet. And u2 is initial velocity of the gun. Okay, so that's what, and before firing these two values will be 0. Will you agree with this or not? Before firing, the bullet will be at rest inside the gun and the gun also will be at rest. That's what u1, u2 will be 0 initial before firing. I'm writing here u1 is equal to u2 is equal to 0. So that's what before firing. And after firing, what happens? Bullet will move with the velocity v1. So what is that v1? v1 is the final velocity of the bullet, right? And v2, that's what? Action and reaction, because we had already discussed about the terminology called recoil velocity in Newton's third law of motion. When you fire a bullet, when you fire a gun, what happens? The gun moves forward when you fire a gun, bullet moves forward and the gun moves backward. right? Because of action reaction forces. So the backward moving of this gun is called recoil velocity of the gun. Okay, so now this V2 is what? Final velocity of the gun. Final velocity of the gun, and this final velocity of the gun is called recoil velocity. What is it called? Recoil velocity. Alright, are you ready now? How to find this recoil velocity? By using law of conservation of linear momentum, you can find the recoil velocity of the gun, right? It is so simple, and let's apply law of conservation of linear momentum. m1u1 plus m2u2 is equal to m1v1 plus m2v2. Okay, here previous case, while explaining the law of conservation of linear momentum, we had considered before the collision and after the collision. Here it will be just like a before firing and after firing, right? So before firing, I had clearly mentioned initial velocities of bullet and the gun will be 0. m1 into 0 plus m2 into 0, it will be 0 here, and it is m1v1 plus m2v2. Is it clear? So here I can clearly write m2v2 is equal to minus m1v1. What I can write? v2 is equal to minus m1v1 by m2. See the interesting part. This is an expression for a recoil velocity of a gun. What is the expression of the recoil velocity of a gun? Minus m1v1 by m2. Let's write the same here. Recoil velocity of a gun is minus m1v1 by m2. Okay, clear? Now, what is this m2 here? What is this m2 here? Mass of the gun. Yes or no? So this m2 is mass of the gun, and this v2 is recoil velocity of the gun. And these two are inversely proportional. If you carefully observe, you'll understand this, right? So recoil velocity of a gun is inversely proportional to the mass of the gun. When the mass of the gun is less, recoil velocity of it will be more. That's the reason. See, if you're associated with NCC or Scout training, you might have seen the guns, right? So whatever may be the gun, that may be the rifle gun or that may be the handgun, whatever it may be. So for example, take the condition of the rifle gun. So it will have so much weight or mass just because to decrease the recoil velocity here, right? So when gun is having more mass, what happens? Its recoil velocity will be less. So when you fire, so you will be keeping the shoulder, right, as a base. So and you will fire it. And what happens? Due to the recoil velocity, the gun will forcefully strike the shoulder when its mass is less. When its mass is more, recoil velocity will be less. With the less velocity only, gun will recoil and hit the shoulder. There won't be any problem to our shoulders. That's the reason. Guns will be very heavy, right? Just to decrease the recoil velocity. Okay, clear? So that's the first application. And how the questions will be asked here? Simple. They'll give a mass of the bullet, velocity of the bullet, and mass of the gun. You can find directly the recoil velocity of the gun, right? And number 2, what's the second application? The second application is the rocket propulsion. Are you ready? Similar way, let's understand the rocket propulsion case. So simple here. This is what the rocket, right? It's not a Diwali rocket. Imagine it's a rocket which is sent by ISRO, NASA people, right? Of course, the same Newton's third law phenomenon takes place and applicable in this Diwali rocket even. Okay? Now, so inside the rocket there are some gases present here. That's called the fuel. And before the firing, right here, bullet is equal to here fuel. That's it. So m1 is a mass of the fuel, m2 is mass of the rocket. Initial velocity of the fuel, initial velocity of the rocket. So when the fuel comes out in this way, rocket moves forward. So simple, right? So now let me write the same thing. What is m1? Mass of the fuel. What is m2? Mass of the rocket. Mass of the rocket. And next, initial velocity of the fuel and rocket before firing is 0. Yes or no? Before firing, initial velocity of the fuel and initial velocity of the rocket is 0. After firing, they starts moving, and V1 is final velocity of the fuel or the gases which will come out because of the reaction force. The final velocity of a rocket will move forward in this way with a speed V2, and the fuel will be coming out with a speed V1. Okay. So here also you can apply law of conservation of linear momentum. M1 U1 plus M2 U2 is equal to M1 V1 plus M2 V2. So this term will become 0 because the complete term is associated with the rocket and before firing. M1 into 0 plus M2 into 0. So the total left hand side will become 0, which is equal to M1 V1 plus M2 V2. Here also velocity of the rocket because of the reaction force, recoil velocity of a gun because of the reaction force, and V2 is equal to minus M1 V1 by M2. Similar concept of the recoil velocity of a gun. There is no difference at all between the first two applications. But the question can be asked similar to that, right? And the most important application of law of conservation of linear momentum, and most of the times the question was asked on this common velocity, right? Are you ready? What is this common velocity? Imagine there is a bullet. Forget about the gun. There's a bullet which is moving with some initial velocity u1, and there is a wooden block which is hanged here. There is a wooden block which is hanged here. Initial velocity of this wooden block, imagine it's a second body. It will also have some mass. Okay. So mass of the bullet is m1, mass of the wooden block is m2, and initial velocity of the bullet is u1 and initial velocity of the wooden block is 0 because it is rest initial. When you fire a bullet here, it will embed into the wooden block of huge thickness I have considered. Okay, it will be embedded into the wooden block. Okay, so what happened after piercing into the wooden block? For example, look at here, this bullet is moving with so much linear momentum and it will be fixed inside, and the wooden block and bullet together move with some common velocity for some time. Yes or no? Can you imagine the situation? Imagine a situation, so there is a bullet which is moving faster towards the wooden block which is hanged somewhere. When the bullet pierced inside the wooden block, what happens? For some time, both bullet and wooden block together, they are inside now, right? They are embedded. So when this bullet embedded in the wooden block, for some time both will move together for some time with some velocity. So that's called common velocity. That's called common velocity. In our easy understanding, let's start. So this is m1 with moving with the speed u1, and m2, and this is u2. Okay. So this u2 may be at rest or may not be at rest. Before collision, so they are moving in this direction. They are moving in this direction. This may not be moving. Okay. After the collision, what happened? After the collision, so this is m1 and this is m2. Both are sticking together. Okay, I'm writing here. Both are sticking together and moving with a common velocity. Imagine that's a common velocity called v, right? Capital V. Before collision, they are moving. This may not be moving. After collision, both stick together and moving with some velocity. That's called the common velocity. So before the collision, law of conservation of linear momentum, let's apply. m1 u1 plus m2 u2, which is equal to m1v1 plus m2v2, and let's apply this here. Initial case same, m1u1 plus m2u2, which is equal to, here m1 is moving with what speed? V, capital V, plus m2 is moving with what speed? Same, capital V, alright? So this is m1u1 plus m2u2, which is equal to V. If you take common, it will be m1 plus m2, right? This common velocity if I write, so that is numerator m1u1 plus m2u2 divided by m1 plus m2. Okay, so this is called the common velocity term. Common velocity term. So if you apply our first case, our first assumption in this, what happens? Our first assumption in this, what happens here? Common velocity of the bullet and the wooden block will be u1, m1 u1 plus m2, and u2 is at rest. I told you, if you consider this case, this is what a case I have given, not in all the cases it takes place. A case I have given. So m1 u1 plus, this is 0 divided by m1 plus m2, and the final expression will be m1 u1 by m1 plus m2. Alright? Clear? This is what the common velocity condition generally we observe in most of the cases in our daily lives. Imagine there is a car which is at rest. There is a big lorry which is moving with some linear momentum, strike this car which is at rest, or collides this car which is at rest, and what happens during the collision and after the collision? Both the bodies move together with common velocity for some time, right? Clear? That's called the common velocity here. When you are playing carom board, what happens when you strike a coin? After the collision, sometimes, most of the times it's possible, after this collision, both the coins will move with the same speed for some time. So that's called the common speed or common velocity. Clear? I hope you understand the three major applications related to law of conservation of linear momentum. Let's solve some kind of numericals related to the law of conservation of linear momentum here. Hey students, let's continue the numericals of the applications of law of conservation of linear momentum. A bullet of mass 100 grams is fired from a gun of mass 20 kg with a velocity of 100 meter per second. Calculate the velocity of recoil of the gun, right? Imagine mass of the bullet is equal to, what is the mass of the bullet here? 100 grams, which I can write it as 100 into 10 raised to minus 3 kilogram, because rest everything is given in SI units. You can see this mass 20 kg SI unit, and this is meter per second SI units. That's the reason I have converted this into SI unit. I've told you many times, I suppose I've informed you already. I've seen students in repeated course, even after their second PUC course, even they are doing the common mistake called the silly mistakes of unit conversions. Convert all the units into one system, right? So that's the reason I have done that. Now, 100 gram is fired from a gun of mass, so mass of the gun, what is that? 20 kilogram. No need to convert this, already it is in SI unit. With a velocity of 100 meter per second. So bullet is moving with a velocity. So initial velocity or final velocity? Initial velocity means before firing. Final velocity is after firing. Okay. So final velocity of the bullet. So they have given, which is equal to 100 meter per second. Now calculate the recoil velocity of the gun. So recoil velocity of the gun, final velocity of the gun they are asking. We know the formula m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Is it clear? So that's what the law of conservation of linear momentum. Initial velocity of the first body and initial velocity of the second body is 0 because before firing, bullet and gun will be at rest position. So 0 is equal to m. First body, let's see, mass of the bullet, okay, into velocity of final velocity of the bullet plus mass of the gun into final velocity of the gun, right? So this product plus this product, and this product what I can write here, so mass of the gun into final velocity of the gun, which is equal to minus mass of the bullet into velocity of the bullet. So you can write now final velocity of the gun, that's what the recoil velocity of the gun, minus mass of the bullet into final velocity of the bullet by, what is this? A mass of the gun. Okay. This is what the formula what we have discussed. V is equal to minus m1 v1 by m2. This is v2. Okay. This is what the formula we had discussed during the theory. I just wanted to write once again the same formula. Let's substitute everything. Velocity of the gun, which is equal to minus, what is mass of the bullet? So this is mass of the bullet. So 100 into 10 raised to minus 3 into what is velocity of the bullet? So it is 100 here divided by what is mass of the gun? Mass of the gun is 20. Okay. So this is minus 10 square into 10 square is 10 raised to 4. See, 100 10 square and this is under 10 square. 10 square, 10 square, 10 raised to 4 into 10 raised to minus 3 divided by 20. And what you can write here? Minus 10 raised to 4 minus 3 is 10. Right? So by 20 and 0, 0 gets cancelled and the recoil velocity of the gun is how much? Minus 1 by 2. It's minus 0.5 meter per second. Okay? Clear? This is the concept of recoil velocity of a gun. Let's see one more numerical. Two objects each of mass 1.5 kilogram are moving in the same straight line but in opposite directions. Okay. The velocity of each object is 2.5 meter per second before the collision, during which they stick together. Right? So before the collision, during which they stick together. So what will be the velocity of combined system after the collision? Okay. What happens here? The velocity of each object is 2.5 meter per second before the collision, during which they stick together. This is what the situation. M1 U1, M2 U2. So this is during collision, M1 M2, and this is after collision. Okay. So they move with a common velocity. That's a common velocity they are asking. Is it correct? Two objects of each mass, this M1, it's 1.5 kg and this M2 is also 1.5 kg. They're moving in the same straight line. Yes, this is the straight line, but in opposite direction. This is the important thing. But in opposite direction. So this M1 is moving in this direction, M2 is moving in this direction. See here, they are moving in opposite directions. Okay. So if you consider this velocity is positive, this velocity must be negative because they are in opposite direction they are moving. Now, common velocity formula is what? M1 U1 plus M2 U2 divided by M1 plus M2. This is the common velocity formula. From where you got this equation? So this is the equation you have got. M1 U1 plus M2 U2 is equal to V into M1 plus M2. This is what? From here only you got this equation, common velocity. Common velocity is equal to M1. What is M1? 1.5 into U1. U1 is what? With what speed they are moving? Each velocity is 2.5 meter per second. 1.5 into 2.5. Right? Now, M2 1.5, U2 is again 2.5. but it is in opposite direction. As u2 is opposite direction, I am writing it minus 1.5 into 2.5 divided by m1 plus m2, 1.5 plus 1.5. See here, 1.5 into 2.5 minus 1.5 into 2.5. So this value minus this value will be 0 because both are same. So v is equal to 0 by 3, which is 0 meter per second. What is the common velocity of the system after the collision? What is the common velocity of the system after the collision? They will be at rest. They will never move because 0. The body is coming to rest. Look at here. Both are having same masses. Both are having same velocities. After the collision, they stick together and come to rest. They stick together and come to rest. That is what I am writing here. If two bodies of same mass, masses are same, velocity is also same, when they are moving in opposite directions, okay, after the collision, they come to rest. After the collision, what happens? They come to rest. After the collision, they come to rest. Okay, so this is what the conclusion for this numerical. We should not only concentrate on what is the common velocity. It is 0. 0 means what? They will come to rest. When they will come to rest, without solving all these things, you can solve the question in objective type questions in this way. If the masses are same, if they are moving in opposite direction, after the collision, they will not move. They will come to rest. Okay? So this is how numericals also will be asked. In the next session, some more numericals will start on the same topic called law of conservation of linear momentum.